Before we took the break, our focus was on deriving properties of mutual information and relative entropy. And in particular, there is one property of relative entropy, which is this Donsker-Verdun lemma, which is sort of widely used. In fact, every paper I have seen where there is a connection between generalization error and mutual information, it's just a clever application of the Donsker-Verdun lemma. And there is a whole bunch of papers out there now, and so I will discuss a few. If we don't finish today, we'll continue next lecture. So so remember the setting we had before. There was a training set S, which is of the form Z1 to Zn, sample IID PZ. So you take S, you pass it through the learning algorithm, P of W given S, and you produce an output weight vector W. And we wanted to with the quantity we were interested in was gamma of P of W given S and PS, which was defined to be E in of W. And remember, E in depends on S, the training error, minus E out of W, which only depends on the marginal of W. You take the absolute value and you take the expectation over S and W. This is what we are interested in bounding, right? And what we want to show is that gamma of P of W given S and PS is less than this quantity, 2 sigma square over N, I of W and S. This is our aim. So we'll start with the Donsker-Verdun lemma for a particular relative entropy term. We'll start with P of S given W equals W. Let's say we have some realization of W. We look at the relative entropy between this and PS. So suppose here what we are assuming is that W is some fixed output. So we fix some output W, and we look at the relative entropy between the conditional distribution of S given W and PS, which is an IID product distribution. S is IID, PC. Okay. And we want to apply the Donsker-Verdun lemma to this quantity. Now note that, before we do that, note that if we take the expected value over W of this quantity, what will we get? Do you remember what this is? We're taking the relative entropy between the conditional distribution and PS, the unconditional version. So this will be random because W is random, right? So we take the expectation with respect to W. Everybody remembers what this is? It's the mutual information, exactly. It's the mutual information between W and S, which is a quantity on the right hand side here. So we will first do the analyze this quantity for fixed W, and then we will bound it, and then later on we will so we will use the Donsker-Verdun lemma to lower bound it, and later we'll take the expectation with respect to W on both sides to get the mutual information term. That will be how these proofs work. Okay. So we apply the Donsker So this we know is greater than the expected value of the function. The function is with respect to S. P of S given W equals W. This is my P distribution. Okay. So the random variable for which the relative entropy is computed is S. Okay. This is P of S given W, where W is fixed and PS. So W is fixed throughout, so I'm not going to parameterize with respect to W. But the understanding is everything can depend on W. Minus log expected value over PS of e to the f of s. So this is my P distribution, and this is my Q distribution in the Donsker-Verdun lemma. So for any function f, I take the expected value of this with respect to P minus log e to the f, and then the expected value with respect to Q. Q is PS. Okay. So what function do I use? Now the trick is in choosing the right function. So f has to be related to the loss function that we want to bound, right? The idea is f here will be computed, the expectation will be computed with respect to s given w. Here it will be computed with respect to just the marginals, right? And then when you take the expectation with respect to w, this will be over the joint distribution, while this will be with respect to some product distribution. It's a little bit inconvenient because of the log, so we'll have to address it, but roughly speaking, this is an expectation with respect to the marginal of S. This is an expectation with respect to the conditional of S. So when you take the expectation with respect to W, this becomes like the training error term, and this would be like the test error term. But we have to choose F so that we somehow don't get stuck with the log. So the way that is done, at least in the first paper by Russo and Zhu, was like this. They take the average of the weight with respect to Zi. Okay, this is our training error. And then we subtract out the expected value of the loss with respect to Z. Here W is fixed. So this is basically integrating this with respect to PZ for a fixed W. And this is taking the average of the loss with respect to the training points. This is the F that we are going to use. S means that it's dependent on Z1, Z2 up to Zn. I should strictly speaking write this as S comma W if you want, but W is fixed throughout. So it won't matter. That's why I did not write W in here. So this is now taking W and EZI, taking the average, and subtracting EZ of L of W and Z. So notice that these terms are all fairly standard. We know what these terms are. Can anyone know say what this is in terms of the quantities we have seen before? This is, so for a fixed Z or for a fixed W, we are taking the loss of W and Z, which is like a fresh sample. Z is not dependent on W. So this is, remember this is by definition the integral of PZ L of W Z dZ. So W is some weight vector coming in, and I'm evaluating the expected loss with respect to a distribution Z, which is the same as my training distribution. What is this? E out. Okay, so this quantity is E out of W. What's the first term? Again, W is coming in, and I'm evaluating, like W is what I'm producing from my algorithm after observing S. It's E in. And lambda is some quantity we can tube. So lambda is just a constant. So f of s here is lambda times E in of W. I'll put S here just so that you remember it's a function of the training set, minus E out of W. So for a fixed W, E out is deterministic, and here W is fixed. Whereas here E in is a function of W. Also note that I can write f of s as lambda times 1 over n, summation of I going from 1 to n, L of W Zi minus expected value over Z of L of W and Z. This is my definition of f of s. I can just take this inside the summation because it's a constant term, not dependent on I. So I'm just subtracting this term over and over n times and hence dividing by 1 over n. This is the same as this. Is clear? Now if L of W Zi is sigma square sub Gaussian, what can we say about f of s? So here W is fixed in the definition of sigma square sub Gaussian, right? So what we know is, since L of W and Z is sigma square sub Gaussian. This is true for each I, so I'll put the index I here. That is expected value over PZI, which is fixed now. PZI is the same as PZ, so I can remove this is same as PZ because ZIs are IID. E to the lambda L of W Zi minus expected value over Zi of L of W Zi. Okay. If I complete the whole expectation, this is less than e to the lambda square sigma square by 2. We assume this in the very beginning. Our loss function, W is some fixed value. The loss function with respect to the distribution P of Z is sigma square sub Gaussian. Okay. Now then it so happens that since f of s is a sum of this n Gaussian of this n terms where Zi's are sampled IID, it so happens that if you look at expected value of Pz of e to the f of s, this will be less than e to the lambda square sigma square by 2n. So if your original loss function was sigma square sub Gaussian, fs, which is the average of n independent random variables, ends up being sigma square over n sub Gaussian. It's the same thing that the variance decreases by 1 over n if you average n random variables. Proofs are again pretty straightforward, we won't do it, but this is just a fact that fs, now this is with respect to pz, that is important, not p of z given w, right? Because here we are fixing w, sampling zi's IID according to pz. So with respect to pz, this loss function is going to be sigma square over n sub Gaussian. You can either do it as an exercise or you can check any reference. This is a standard fact that if you're averaging n random variables, then they become sigma square by n. Each is sigma square sub Gaussian. They become sigma square by n sub Gaussian. Okay. So now we want to apply Donsker-Verdun lemma to simplify this quantity. So remember, we have to compute this quantity, and so this I can also replace this Pz by Ps, because S is just an IID. It consists of n copies IID Pz. So I'm just going to write it as Ps to be fair. So we want to evaluate, again let's go back to this quantity. We need to evaluate two quantities. One is expected value of P of S given W of f of S, and the second is expected value over Ps or log of this of e to the Fs. So this one is immediate because Fs is sigma square sub Gaussian or sigma square by n sub Gaussian. When we take the expectation with respect to Ps, we have this bound. So this part follows immediately. So we know that this quantity is greater than lambda square sigma square by 2n. So the trick here, what they did was, they just used this sub-Gaussianity assumption, or more generally the assumption that you are on some support, to easily lower bound. The log would have caused a lot of problems in the bound, so they got rid of it. The log of the expectation can cause problems, so they got rid of it by making it lower bounded by some constant term that we didn't have to worry about. Okay? For the first term, we are in luck because this is the difference between E in of W. This is E in S of W minus E out of W. This is the first term, right? F of S, we showed by definition, is the difference between the training error and the test error. So the first term is, now we are taking the expectation with respect to P of S given W. So what we will do is, we will for now define delta of W to be the expected value of P of S given W of E in of S of W minus E out of W. Just define it right like this. We'll later take the expectation with respect to P of W, and that will be what we care about, the joint distribution minus the average test error. So what we have shown, that the relative entropy between P of S given W and Ps is lower bounded by lambda times delta of W. We had the lambda term here, right? So there was a lambda here, and F has a lambda in front of it, okay? Minus lambda square sigma square by 2n. This is for all W. For any fixed W in W, this is what we show. And we can, this is true for any lambda in R. For any real number, this is true, that the relative entropy is less than this quantity. And so in particular, we can optimize this and select lambda to be n delta of W by sigma square. If I try to take the derivative, set it to 0 and find the best lambda, I will try to get the tightest lower bound. It so happens that what we need to do is set lambda to be n delta W by sigma square. If you do that, what we have is d of p of s given W, Ps is greater than n delta square W by 2 sigma square. If I substitute this in here, it's one candidate, then I get this lower bound. So we have transformed the Donsker-Verdon lower bound by selecting a particular function f, which is related to the loss function in our application, and connect the relative entropy with the gap between the training and the test error. So since we are interested in taking the expectation here, we will rewrite this as delta of W is less than square root of 2 sigma square over n, the relative entropy between P of S given W and Ps. Same thing as before. Okay. So what we have here is, this is the expected value of S given W, E in of S and W minus E out of W with the absolute value, right? So let's take the expectation now with respect to W on both sides. So now taking what we get is that the expected value over S and W of E in of S of W minus E out of W. This is the generalization error that we wanted to compute. Okay. This is the gamma of P of S given W and Ps. This is less than the expected value over W of square root of 2 sigma square over n d of P of S given W and Ps. So what do we do next? Can anyone see how we take this expectation inside? So if we can take the expectation inside, then as was observed before, this becomes the mutual information between S and W. So how do we take the expectation inside? So remember, if you think of this as some function g of x, so let's say g of x is root x, we want to take the expectation inside the square root, right? So what kind, do we get an upper bound or do we get a lower bound? So imagine this is the function gx, it's a concave function, and we are currently taking the expected value of this function gx. If we take the expectation inside g, do we get an upper bound or a lower bound? So think about it. Imagine you have 2 points, right? Like this. If I take the expected value of gx, then I'm drawing a line and taking the value in the middle. If I take g of ex, then I'm first taking the midpoint. This point is always smaller than any point on this line. If I take the expected value of x, I will get some point here, and then I compute like g of ex will be some point here. So this is known as Jensen's inequality. So this implies that this is going to be less than square root of 2 sigma square by n EW of D of P of S given W and PS. This is an inequality that has a name. This is Jensen's inequality. It says that if you have a concave function, I'll write it here, if Gx is concave, and you take the expected value of Gx, that is always less than G of the expected value of X. So that's what I'm doing here. So this is a concave function, square root. So if I bring the expectation inside, I get this. And this is my mutual information between S and W. So this gives me finally, now the left hand side when I take the expectation was this gamma term that I wanted to bound. Thus, what we have shown, gamma of P of S given W and PS is less than square root of 2 sigma square over n I of SW. This was a result first proven by Russo and Zhu in 2016, and later it was reinterpreted nicely by Zhu and Raginsky. So this is the first result, the first paper. So any questions about this? Steps? Any implications? Any comments? I would like to hear your feedback because I'm teaching this for the first time. I'm also learning with you. It's not like I know these things very well. It's fairly new stuff. So if you have any comments, thoughts, good to hear. Is it too dry, the proof? So for me, like what I find is it's just like one clever application of this Donsker-Verdun lemma. And when we first saw it, we thought it was something that, happens to be the case. How tight is this bound? We don't know. It's not even clear if you can evaluate it because it requires a lot of effort. You have to compute P of W or P of S given W. Computing the mutual information is not that easy. The early examples that came out were very, very simple examples, like for which you could compute these quantities and just establish that this bounds make sense in corner cases and so on. But more recently, there has been, like in the last 2-3 years, more sort of interest in these. Like when people looked at things more closely, like they showed that, you can tighten these bounds, you can apply them to SGD type algorithms. So this is something one of my students was involved in, and me and my student, along with some other people, we applied this bound to analyze the generalization error for SGLD recently. And even beyond that, more sort of results have come out, as like one very interesting paper came out last week. So I think there is still a growing interest, but you have to be very clever and careful in how these bounds are applied, like to get new results. If we just look at the expression at the first glance, it might not mean much. Even computing this quantity itself, like, is what do you do with this quantity, right? It's nice to have a mutual information, but how do you compute it? And initially, we all struggle to even use these bounds properly. So I'll tell you one other result that came out. I think this is by Bu et al. In 2019. So this appeared last year. And they tightened the bound by showing that gamma of PS given W and PS is upper bounded by 2 sigma square by n. But instead of taking the mutual information between the weight vector and the entire training set, they did the summation of n going from 1 to n, I of Zi and W. So you take the mutual information between each individual sample and the weight vector. Here you're taking the mutual information between the entire n samples and the weight vector. So if the weight vector is, for example, some sort of a deterministic function of these samples, this can be very large, of all the n samples. Here you are taking the mutual information between each individual sample and the weight vector. And so this means that this is going to, but then you have to sum over all n terms, right? You take the average of all those n terms. You can show that this quantity in general is going to be smaller than when S is IID. You can show that I of SW is going to be smaller than this sum. Since S is Z1 to Zn, which is IID PZ, one can show that I of SW actually is greater than the summation of n going from 1 to n, I of Zi and W. So this bound is strictly better than this bound. This is again an easy exercise. When S is IID, you can use standard properties of mutual information to show this. So as a result of this, they showed that first, and they give examples where this sort of gives us better generalization error than the previous bound. So I'll show you how this is proven next. It's again pretty much the same proof with a small modification of how Donsker-Verdun lemma was applied. So note that if you look at I of W and Zi, this is the relative entropy between P of W and Zi and P of W, P of Zi. This is a definition of the mutual information, the relative entropy between the joint and the marginals. And also we can write it as EW of P of Zi given W equals W and P of Zi. You have seen all this before. So now I will start by applying Donsker-Verdun lemma to this term and then choosing the function f properly. We know that this is greater than E P of Zi this minus log EQ, or Q is PZI for us, e to the f of Zi, okay, for any Fi. So again, f of Zi is the random variable of interest. Okay. We are computing the relative entropy between this distribution of Zi and this distribution of Zi. So our function is dependent on Zi. So what we can do is say is for any function f of Zi, this lower bound holds. That the relative entropy between these two terms is less than the expected value of f of Zi with respect to P of Zi given W minus log EP Zi e to the f of Zi. Now the question is, what f of Zi do we choose? We will choose the one that will naturally result in the generalization error. So what f of Zi do we choose? Well, f of Zi that we will choose is lambda. Again, there is this one sort of free parameter we have, the lambda, that we optimize all the time. L of W and Zi minus expected value over Z of L of W and Z. So this is the choice of F. Before we had L of W and S, which was the training error on all the points. This is the same term as we had before. This is our E out of W, right? The idea is you will apply the Donsker-Verdun lemma here, then average out across all the, take the expectation with respect to W. So we get a bound for one of them, then average out over the ZIs. So we get E in here, and this becomes the average of the mutual information. That's the idea. We'll do per sample lower bound using Donsker-Verdun lemma, and then average across the samples, and that gives us the Bu et al. Result. Okay, so we have this. Now we do know that if you look at this quantity, log E P ZI e to the lambda L of W ZI minus E Z L of WZ. We know this is less than e to the lambda square sigma square by 2 by the sub-Gaussianity assumption. The second term is again set in exactly the way you want, so you don't have to worry about the log of the expectation. It can be simplified by the sub-Gaussianity assumption, and it is upper bounded by e to the lambda square sigma square by 2. Because this is exactly how the loss function is designed. F of W, L of W ZI minus EZ L of WZ. So W is fixed. The important point is this is the marginal distribution. So the sub-Gaussianity assumption is defined with respect to Z for any W. So this holds. For the first term, what can we say? For the first term, we'll define delta I of W to be expected value of P of Zi given W, L of W Zi, okay, minus expected value of Z. This is E out. I'll just write it like this. Okay. Then what we have shown is that the relative entropy between D of Zi given W equals W and P of Z, which is same as P of Zi, is going to be lower bounded by lambda times delta I of W, okay, minus lambda square sigma square by 2 for all lambda in R. So we do the same trick as before. We optimize over lambda. So we set lambda to be delta I of W by sigma square, okay, and so we get D of P of Zi given W equals W, and P of Z is greater than lambda square or greater than delta I square W by 2 sigma square. Or what we have shown is that delta I of W is less than square root of 2 sigma square D of P of Zi given W equals W and P of Zi. So this is more or less the same steps after we define the loss function as the original proof. The only difference is we don't have sigma square by n here because we only are taking the sub-Gaussianity with respect to one Zi, not the average across the n samples. So that's the only difference. It's exactly the same steps otherwise. I think in hindsight, this is perhaps a simpler proof than the previous original proof. Okay, so now what we will do is we will take the we'll now take the average across all the n samples. Doesn't matter which order you do. What I will do is I will write this like this. Just averaging. Now we can add delta I is for the ith sample. So we are just averaging across all the n samples. And now I'll take the expected value over W with respect to W on both sides. So I'll rewrite the same inequality from the previous page again, but with expectation over W. So let's look at each of the sides. Let's look at the left-hand side. Okay. The left-hand side, we get the expected value over 1 over n, summation of I going from 1 to n, expected value of P of Zi given W, L of W Zi minus E out of W. Okay. So when you bring the W inside, so I can write this as 1 over n summation of I going from 1 to n, expected value of Zi and W of L of W Zi minus expected value over W E out of W. Just distributing the expectation, and then EW P Zi given W is this. But note that the first quantity is exactly expected value over S and W of E in of S and W. Okay. Because when you take, this is your training error. If I were to take the expectation here outside, I get 1 over n times the summation of I going from 1 to n, L of W and Zi. If I do one more step, if I take the expectation outside, then I have to take the expectation over Z1, Z2 up to Zn comma W, which is the same as E of S and W. When I bring the expectation inside, for this term, I can integrate out all the Zi's except the ith term. So these two are the same. And the second term is just E out of W. So this is the quantity we wanted. E of SW, E in of S and W minus E out of W. So it does not matter how you take the average, how you take the expectation, they all commute basically. Okay? So now we have to look at the right hand side, and we want to show that this quantity is less than the bound they had. This is less than 1 over n, summation of I going from 1 to n, square root, which was, no, they had a slightly different bound. It was square root of 2 sigma square by n, summation of I going from 1 to n, I of W Zi. Okay, so it's basically applying Jensen's twice to get to this bound. Okay, so first what we will do is the right hand side is E of W summation of I going from 1 to n, square root of 2 sigma square d of p zi given w pz. First, I will use the fact that I will apply Jensen's here. and bound this as E of W square root of 1 over n summation of I going from 1 to n 2 sigma square d of p of zi given W and p of z. Because again, if I have, say, a bunch of numbers x1, x2, x3, and in one case I'm taking this sum and then averaging it out. In the other case, I'm taking the average of x1, x2, x3. I'm taking these three and averaging out the values. That's one term. The other is taking the average of x1, x2, x3 and then computing the function. And so that is always going to be greater than the sum of the averages. Right? That's the Jensen's for concave function. And then I can bring the expectation inside the summation as well. Again, the same idea by Jensen's. I'll put 2 sigma square here, summation of I going from 1 to n, EW, and this is, since P of Z and P of Zi have the same marginals, I can put Zi there, I of W and Ci. So again, just a small observation. Let them get this paper. Like they just basically said that instead of applying the result at each on using all the n samples, do it on a sample by sample basis. So that allowed them to get this result. Since then, many other variations have been developed just by a clever application of the Donsker-Verdun lemma. So here is a more general bound. You want to bound this. We can bound this by expected value. So this is a quantity we want to bound over J and some set Sj. So first write down the bound and explain what the terms are. Square root of 2 sigma square over n minus m I of Sj complement W given Sj equals little sj and j equals j. So here j is a random set of m indices of S. Sj is the subset of S with these j indices. So the idea here is, and Sj complement is Sj is S minus Sj. So the idea is that you can select any random set of m indices. M could be 1. So you could select 1, or m could be n minus 1. All of the options are possible. So you can take any set of m indices. You can condition your mutual information assuming that these j indices are available in the conditioning. And then you take the mutual information between the weight vector and the remaining elements. So you compute that, you have to scale it appropriately, and then you take the expectation with respect to j and Sj. It's a little complicated, but the main value of this is this allows us This sort of conditioning has been proven to be useful in order to evaluate the mutual information using data-dependent estimates. So one of the challenges is, and we'll do an example later on how to evaluate, why do we care about such bounds? Well, what are they good for, right? So it turns out in certain examples you can compute them explicitly, but in general it's hard to compute. So, however, what has happened recently, and this is actually our paper on new ribs, mostly the work done by two of our students, so I don't take much credit. Uh, so in this work, we took one step forward and we said that if you want to properly evaluate the mutual information bounds, you can somehow tweak the existing bounds in a way that you have to condition on some of the elements. Like here we can take j in this example, the easiest way is to take j to be n minus 1. So you can condition on all the remaining, all but one example from the training set and look at the mutual information between the model parameters and the missing example. You can compute that. If you can get a good estimate of that, and we proposed a way to do that, using the variational bounds on mutual information, and then take the expectation over J and Sj outside, then average over all the different subsets. This can give us very much tighter bounds than what people had done. So what happened is, for a long time people had these sort of bounds. They were trying to get tighter and tighter bounds. So there were some papers that considered alpha mutual information here, upper bounds using alpha mutual information and so on. All those bounds were good in principle, but very hard to evaluate for for practical models we care about. As a result, in this paper, we put forth a method to evaluate this mutual information using what is called data-dependent estimates. And this allowed us to show that the bounds that we are getting here, in fact, are far more tighter than what people had previously done through conservative analysis. And sort of that created some interest in the field. Hopefully it does. So I won't go into the details because it's a little tricky. I have posted the paper online if you want to read it and understand it more and discuss and do some project. I'm happy to talk to you about it. It's a little tricky. The notation already you see is complicated, so I won't go into full details, but you're welcome to look at it. So where we will go next is, there is a very recent paper that came out last week. Let me see if I have the authors. It's a paper I posted on the web page. I don't have the name of the author, but I think it's posted. So this appeared in Jan 2020, just last week, the last week of January. And they developed a new bound and they had a slightly different, like the way they set it up was slightly different than this bound. All of these papers were looking at just one quantity, essentially the mutual information between the model parameters and either one training sample or the entire data set or a subset of training samples. So the idea was how much information about the training set is contained in your model parameters. So this was sort of the line of thinking. This paper changed the game slightly. They said that suppose our training set, suppose we have 2n samples. Which are sampled IID PZ. Okay. Our training set is of n samples, but it is constructed like this. Suppose I have UI to be IID Bernoulli half random variable for I equals 1, 2 up to n. And the training set is selected like this. If ui is 0, then tau, the training set, will have tau union zi. We put the ith example in the training set. If ui is 1, then tau will take tau union zi plus n. So at each time we have two choices, either to include zi in the training set or zi plus n, but not both. This is the idea. We select one out of the two at random. And then tau is as the input. It again has IID n examples. We pass it through the learning algorithm. P of w given tau, and you produce w as the output. So what was shown was that the generalization error between P of w given tau and P tau. So note that P tau is still IID PZ despite this construction. So it's the same setting as before. But what they showed is if you look at how the training set being constructed in this way, you can upper bound the generalization error by 2 over n I of u. There's a sigma square, again, if you make the sub-Gaussianity assumption, 2 sigma square over n, I of u and w given d. So this u is the vector, okay? U is u1, u2, up to u capital N. So it's the vector of IID Bernoulli half random variables. Each is 0 or 1 with probability half. U decides what tau is set to be. The entire bound is conditioned on D, so it is conditioned on the 2n examples that you have. So you're going to generate 2n examples and fix them. Now the training set consists of n random examples from this set based on U. So U tells me what is tau. Given D and U, I know what tau is, right? So it is looking at the mutual information between this U sequence and the model parameters given the knowledge of D. Okay, so it's saying given the model parameters and given the set D, which is the 2n examples, how much information can I get about which examples are in my training set? Like what sort of samples were selected. So I'm given 2n examples and I'm told n of these were used for training. My job is to guess, given the model parameters, which of those examples were selected. So they said that this is a quantity that can also bound the generalization error. So this is sort of the new idea. They have a very nice paper. They have lots of cool connections to VC dimensions, differential privacy, and whole bunch of things showing how one implies the other. The problem with these bounds is if W is a deterministic function of S and everything is continuous value, this blows up. Like I of WS can be very large. There is no connection. This is always bounded by the entropy of U, and the entropy of U is at most n because it is a collection of n Bernoulli half random variables. So we have a clear bound on this quantity. Okay? And so that's one good thing, and they actually show that this bound has very nice implications. So they have unified a lot of nice results with this bound. So we could go over, if there is interest, we could go over the proof of this, but the interesting thing is it's just, again, a clever application of the Donsker-Verdun lemma. So if you look at the proof, it's just like you apply this, the Donsker-Verdun lemma in just the right way to get this. It also opens up a whole bunch of other questions. Can we tighten this bound using the kind of tricks that Wu et al. Did for sample bounds? Do we need 2n samples, or can we reduce the number of samples in D and get a similar bound? So all these are interesting questions that are still open. We don't know that. Since the paper just came out, I think there is plenty of opportunity to understand what these bounds are and how we can further tighten it and where they can be applied to. Okay, so a lot of things are still interesting and open here. Now, if there is interest, I can go over the proof of this bound next lecture. How many people would be interested in this? Okay, I think there is a substantial number. It's not too different from the Donsker-Verdun lemma, but if you want to build up on this and connect things, then it will be worth seeing it. After that, I can explain to you how one of these bounds, at least the basic one, is applied to get an upper bound on SGLD. Like bounding generalization error for an algorithm called stochastic gradient descent with some noise. So I can explain to you how that can be done, and you can see how properties of information, mutual information, can be useful there. And we'll stop at that point and then move on to other topics, because then it will be too much to talk about one topic. I do think there is plenty of work, interesting questions still here. Um, I believe I want to select the next topic to be the minimax theory. All of this analysis, all of these results were sort of achievability results in machine learning. We say that there are algorithms that are reasonably good, like the gap between the training error and test error is small under these conditions. So they say what is possible. Minimax results are like converse results in information theory, like saying proving hardness of a problem. We don't want to assume a specific algorithm or a training mechanism. We just want to say, hey, the problem is fundamentally hard. You need way too many samples in order to get any meaningful results. So this is very important. Imagine your boss tells you to, gives you 10 samples and says, provide me state-of-the-art algorithm. You want to prove it's impossible, right? So you need to provide converses. You need to give like sample complexity lower bounds, and minimax theory allows you to do that. The nice thing is, again, property techniques from information theory like Fano's inequality, KL divergence come up naturally in minimax lower bounds as well. So I think that's a natural way to continue this flow. And as I said, the syllabus is not fixed for this course. If there is a particular interest that falls in the theme of these topics, you can talk to me. I can prepare lectures and we can discuss it. Not everything will be 100% smooth because I'm preparing things myself. So I'm only so far ahead of you. But I'm happy to look at topics you guys are interested in. Okay, so I'll stop here. Question?